It's really amazing to be here, but it's also a little, what's the right word I'm looking for? It's a little puzzling to see people complain of heat. I come from Dallas. And this is my spring weather, and I love it. Okay, I love it. I don't even know why people turn on the ACs at this weather. It's just perfect. I finished my PhD at Oregon State, and so this feels like Oregon meeting a coastal town of Oregon, and so it's so beautiful, and it's and people are so warm. So thank you so much for that kind invitation and introduction. And I'm really enjoying my time here. And this is my opportunity to welcome you to really come to Dallas to feel what summer is. My wife just texted me. It was 45 yesterday. Okay, and I was telling them, and we have this annual tradition where they put an aluminum sheet in the windshield of the car, and they put cookie dough on it, and then it gets baked in about 4 to 5 hours. So that's the temperature inside the car. Okay. So with that background about me, I'm going to talk about AI in the loop for healthcare. So I'm Sriraam. I'm a professor. I'm a faculty of computer science at UT Dallas. I need to thank my PhD students because I'm feeling like all the time that I'm stealing their credit. They are the ones who do all the work. So we've graduated about, I think, 12 to 13 PhD students at this point, and we have about 10 PhD students currently. And thanks to all my key collaborators. And I kind of could not list all the doctors that I work with in a single slide without going further away. So thanks to all my clinical collaborators and the funding agencies that have been continuously funding with. So this is who we are, and this is what we do. The way I think about our research is that we are inspired by problems from the outer set of hexagons and develop solutions in the inner set of hexagons. Because one of the earliest advice that I got from my advisor was, do not develop a hammer and then search the nail for it. So we try to do the other way. And so we are, we work on different types of problems all the way from healthcare. As you can see, many of them are listed here. To we also work with logistics. That was one of our key collaborators was moving things around US. We work with actually right now, we are working with veterans for to make sure that they don't have the post-traumatic disorder, and how can we help them come out of it, and veterans who lose their limbs, how can we integrate them to use the artificial limbs using AI. So there's a lot of high impact problems that we are looking at, and we develop techniques all the way from classic machine learning, and by classic machine learning I mean decision trees, rule learning. Okay, for the younger students here, machine learning did not start in 2013. Okay, I just want to make it very, very clear because it's very depressing to read papers where the citations start from 2020. Okay, so when I say classic machine learning, we still do rule-based learning, and it works beautifully on small data sets where you have a lot of domain knowledge. And I want to emphasize that in this talk. We do reinforcement learning. Of course, we do deep learning. Otherwise, nobody's going to give us money. We do optimization and relations and relational learning, and I'll explain all this. But the big agenda that my research agenda is asking this question, which is, can we build AI systems that can seamlessly interact with, learn from, collaborate with? And I added this in the last 4 years, potentially teach back the human expert. Why? Because we made some interesting discoveries that the human did not, I wouldn't want to say the human did not know, but the human was not aware of. They probably had an intuition, but they didn't quite get the connection. And I'll give you some examples of this. So this is what I call as human-allied artificial intelligence. But then we are professors, right? Which means we are always in a constant state of confusion. It's not just an existential confusion, but is this the right definition? Is this what I'm trying to do? Am I doing human-allied AI where they just collaborate with? Or really, should we take a step back and say, what am I doing? Am I doing AI in the loop systems? Because these systems existed before AI. So I find the human in the loop systems a little weird definition, unless it's an AI system that was built and then you added a human into the loop, right? But most of these systems where we get things to work are actually systems that already existed, that we bring AI. So for me, a more appropriate definition seems to be AI in the loop human systems, right? That's really what we are working with. And I want to give you a concrete example. I give this example for the last 10 years, and it's still correctly valid. It's exactly 10 years back, July 2014. I have a very bad history of breaking things, below my belt. And so I went, with a twisted knee to the urgent care. I was a young assistant professor, okay? And I want to emphasize that because I was always on the phone, right? And the doctor is asking me some questions. And I said, yes, 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 yes. And then final question, it is a he asked me, are you done? And I said, yes. And then, my wife was sitting next to me. We were just newly married. She gave me a nice whack in my back. And I turned around and said, what? She says, you have diabetes. You didn't tell him that. And possibly the one single most important information that the doctor needed to know. Why? Because of the fact that I twisted my knee. His first course was to put me on steroids. And that would have shot up my blood sugar level. Hell could break loose. But the doctor was like, whoa, he has diabetes. And he didn't tell me that. Okay, now I'm going to change my plan of action. So obviously he went for some NSAIDs, trying to get some, we'll see how you are doing 2 days. For 2 days, if you're not able to manage the pain, then we'll put you on steroids. And then, I'll bump up your metformin. If needed, I'll give you a short dose of insulin. We'll see your blood sugar level. I'll give you some extra, back then you had to poke still. I mean, now I wear a continuous glucose monitor, but back in the day, you still have to poke 3 or 4 times a day to keep track of your blood sugar. So the point I'm trying to make is that was the moment that hit me that we should start thinking about putting an AI system there. Of course, the biggest problem there was the electronic health record that existed in my hospital was not connected to the urgent care. But let's assume that it was connected. Okay, so if it was connected, then we need to have an agent, and I call it a statistical relational learning agent, Starling agent, because it learns from relational data to build statistical models. Electronic health records are really stored in databases, right? So relational data, you build statistical models, so you call it statistical relational learning. And the way I envision it was the system should say, do you know that Sriraam has diabetes? And you're going for a steroid. Is that the prednisone is typically what they give? So is that the right way to go? And the system should be, the doctor should be able to say, well, he didn't tell me. Thank you for letting me know. Or yes, I'm aware, but he's in acute pain. I want to bring it down first. It's a conversation between an assistant and the doctor at that point. And so so that's the grand vision that we are working with. But again, right, it has to be able to communicate in a language that is understandable to the human doctor and take in back a feedback that is being presented by a doctor, not a machine learning expert. So I'm not going to have somebody sit there, adjust the weights of a neural network when the doctor tells me something. The system has to understand what the doctor is saying to take it back into its internal representation. So you see the problem there. There is a problem of communication. And I know I'm setting the problem up for a longer time. Maybe I'm cutting my technical part short, but I really want to emphasize this point. Communication, when you're building real systems, is the key. I'll give you one more example. There was this professor that I worked with. She's a computer science professor, a high performance computing professor, again, 9 years back. And she and I had a long conversation, 1 hour. We really loved how we were talking. And she's like, okay, give me an algorithm. I said, belief propagation. Let's do belief propagation. We need to scale this up because back then probabilistic graphical models were still very big. So let's scale belief propagation. And she goes, Sriraam, I want an algorithm. I said, belief propagation. And she goes, no, that's an application. Give me an algorithm. So you see the problem there. What machine learning people consider as an algorithm, high performance people consider that as an application. Why? For them, the algorithm was scheduling. They were looking at the scheduling process as the algorithm. Now, this is between 2 computer science professors who are as close as you possibly can, yet be diverse. We have a communication problem. So imagine working with the doctor, right? When they talk of specificity and sensitivity, we have to understand its relation to precision and recall and figure out how we are doing this. So the point I'm trying to tell all of you, primarily the younger ones, is before you set up a meeting with a domain expert, please understand their vocabulary. Okay, otherwise, we realized after 45 minutes, what we were talking were 2 different things. And of course, in the end, I gave her an application. I still couldn't give her an algorithm because I'm not qualified to do that. So with that, what I'm going to do is I'm going to, because my title has healthcare, I'm going to focus on 3 specific problems. The first one is on a cardiovascular health problem. And I'm going to look at one particular data set that we have been working with for about 15, 16 years now. The data is called Cardia. The data was charted in 1985 across 5 centers in the United States. And they brought people who were between the ages of 18 and 30. So these people were between the ages of 18 and 30 in 1985. And they've been bringing them back every 5 years. In the initial part, it was like 2 to 3 years. So 85, 87, 1995, no, sorry, 1992, I think, and then 95, 2000. From then on, it's been every 5 years. So we had the 2020 cohort, we are getting the 2025 cohort. And we started measuring things on these people, right? But initially, we didn't have a lot of things, right? It's 1985. As technology improves, we can measure more and more stuff on these people. Right now, we've started sequencing them. So we actually have sequence data on these people. So, and again, we had 5,000 people initially. Last I checked in 2020, we still have about 3,400 people in the cohort. So that's, if you work with clinical data, that's a reasonably robust size for a population. And of course, they were between 18 and 30 then. So they are between somewhere in 58 to 95 now. Sorry, 58 to 70 now. So they are on the older side. And of course, many of them are starting to have cardiovascular events all the way from coronary artery calcification. And some of them have died also. So we have these record on them. And now you can see how machine learning can help. Can I look back in their data from their teenage or early 20s to figure out who's going to have heart attack in their 70s or 50s? We can ask many types of questions. And I'm going to give you some of the results that we have. And to validate this, because remember, you just don't want to make large conclusions from a small sample. What we try to do is we also evaluate our algorithms on other problems, like Jackson Heart Study is another famous data set out of the Eastern United States, registry data that we have from multiple hospitals. So we evaluate on multiple electronic health records, and we have some results as well. The second problem is something that I'm fiercely passionate about recently, is predicting adverse pregnancy outcomes. Because as I was saying yesterday in Navi's group meeting, that nearly 20% of births in the United States have some adverse pregnancy outcome with it. Nearly 16% of the births in India has preterm birth, not just any adverse pregnancy outcome, but preterm birth. And so this is the case across the world, right? And while I mean it jokingly, it's also true. The one thing that humans have perfected is reproduction. And if we have, and particularly in India, apparently we have a kid born every minute. So when you have that kind of practice, we should be able to do it correctly, but we are not. And that is many choices there, all the way from, their family history to the behavioral data, to the age of the dad. I mean, it matters. All these things matter. And we are trying to figure out where can we intervene to make these things better. Of course, we had a little bit of a difficult childbirth. Our first kid, our only kid, we had some problems there. And so that was also one of the motivation for me to see if we can turn this around. And we have a current running NIH grant, RO1 grant on this. And we've been, and I'll show you some results that we got. And I'll talk about this as well. This is in collaboration with Indiana University Regan Street Hospital. But now we have also started to collaborate with a group in India called Garbini. Again, exactly focusing on similar problems. A group in Brazil, and we are starting to collaborate with a group in Portugal. So this is the type of problem that we are looking at. That's the second problem. Third problem, of course, is electronic health records, because I started my career in a medical school. So I figured out how to denoise electronic health records in the 2.5 years that I was in the medical school. So for me, working with electronic health records is now actually bread and butter, and we can do this reasonably. And we have been working on multiple papers in this as well. So when I think of human allied AI, there are a lot of challenges, particularly in healthcare data, because data is in different types and formats. Like we talked about yesterday, even if it's in tabular data, we have completely different types and formats. And actually what one hospital collects is completely different from what another hospital collects. So for instance, in a country, if we talk at the scale of countries, in US, we score the gestational diabetes right at the 12th week. We see the risk for gestational diabetes. Whereas in India, they actually don't even score it. So we don't even know the prior risk for gestational diabetes. In fact, in many cases, they don't even measure. But Indian women have, because Indian women have a lower risk for gestational diabetes. But if they do get gestational diabetes, there is a higher risk for type 2 diabetes. So there is a lifelong issue that we should intervene with, right? So anyway, the point is that the data is in different forms and types. There are different scales of data. I go to the hospital 3 to 4 times a day. The younger ones here, maybe you go 4 times, in an entire decade. Maybe once in 5 years is what you go to a hospital. So we have completely different data streams. And of course, there is noise. The knowledge, again, knowledge is changing continuously. You don't need to look anything beyond nutrition. Coconut oil, bad. Coconut oil, superfood. Coconut oil, meh. So you get this thing every 3 years. Your knowledge keeps changing. Why? Because new finding comes through. And then you don't know which is correct, which is not. But so we have to still live with it. We have to understand this. Again, think of it in a macroscopic scale. We thought that the earth was flat. And then we know that the earth is round. Atom was the smallest element. No, not anymore. So we kind of like figure these things out as we go, but we are robust in learning at this. And then the other ones are really hard, right? Really hard. We don't even know the long-term effects of running an LLM, with so many trillion parameters, and we don't know the carbon footprint that we are leaving for the next 100 years. So the point I'm trying to make is that as you go down this list, things get harder. But what do you think is the biggest challenge? In my head, it's grad students, because everybody wants to do deep learning. Everybody wants to do LLMs. Everybody wants to do the latest and the greatest. But the best algorithm might be around here. So the greatest challenge for me is actually sitting down with this first year grad student and convincing him or her to work with me. And I'd say, give me some time. I'll convince you that this is the best algorithm. And then we go through this. On the other hand, you convince me that deep learning works great for this one. We'll take it up. So the point is that, again, horses for courses. That's my one recommendation, is we need to think about, before we jump into the queue, is this what we need to do? Okay. But if I think of the 3 steps, I think of it as a ladder. At the foundation, you need to have a strong foundational algorithms. And deep learning could be it, because if you have a lot of images, a lot of MRI images, deep learning could be it. I really don't have a problem. But you have to figure out what is the best algorithm for the problem that you have at hand. And what are the characteristics? The algorithm should be efficient, should be generalizable, should be explainable, because we want it to be at some point interacting with the user. The second step is saying, well, data is not everything, because the data really is focused on a small subset of population, particularly the adverse pregnancy outcome that I'll tell you. I'll give you a bunch of examples as we go, but it's from a university town in Indiana. And its adjacent areas. So it's predominantly white, Caucasian women, either professors or young students, right? So there's also that bimodal distribution when it comes to age. It's not as generalizable. So how can I take something and understand it with respect to the entire population? That's where the doctors come in. And they give you knowledge, right? They are not mere labelers. If I take an example and take this active learning approach and tell the doctor, okay, label this example as positive or negative. So you have 2 hours of your time. I give you 100 examples, label them as positive or negative. You think they're going to work with me? No, they're going to throw me out, right? Their time is important. They can give me knowledge. So we want to do the opposite. We want to say, what can you tell me about this? Tell it to me in English, and I'll figure out a way to translate it. And of course, the last step is, I want to do is actually close the loop. I'm always inspired by my kid, who is now 8.5 years old. We were building Legos during the COVID time. He was around 4 during COVID started, and I was building for him, right? And I said, Pranav, give me this, give me that. And so he used to give me that, and I used to build. Somewhere around 2021, a switch flipped in his head. One day I bought a new Lego set, and I said, come on, Pranav, let's build. And he looks at me straight point blank, and he says, Dad, shh, I'm going to build it. I will ask you if I need help. That was the aha moment, because that was telling me that he knows what he knows. But most importantly, he has figured out when he does not know something. And so to me, that is what we need machines to do too, right? We want the machines to say, okay, I know what I know, but maybe I don't know. And I'll ask you questions. Okay. So with that, let me give you a motivation on why machine learning can work with the personal experience. This was when I started as a postdoc, 2007. At Wisconsin, and we were working with Dr. David Page, and people who are on the older side would remember these COX-2 inhibitors. At least in the US, they were big deal. Vioxx and Dextra. These were typically the ones that were in the US. Essentially, they were provided by the doctors. They were prescribed by the doctors for injuries, muscle injuries, and so on. And they actually, after paracetamol, Tylenol in the US, they were the second highest sold drugs in the market. But somewhere around 2002, they started, zooming in on this drug. And in 2004, they pulled out Vioxx from the market. And in 2004 December, FDA issued a warning, and it said, well, please don't use this drug. And then even after that, 4 months later, they had to pull Bextra out of the market because those guys did not agree. What was the side effect? Heart attacks. There were a lot of heart attacks. So what we did, and this is all credit to Professor David Page, who is now the chair of the biomedical department at Duke. What David and we did was we looked at the data from 1999 to 2002, just 3 years of data from a single hospital in the US, okay, just from one hospital in the US, because remember, this was prescribed left, right, and center back then. And we were able to learn rules. And the rules came out like this, okay? Don't parse it too much, but what it really means is, this is kind of telling you what is the indicator, what predicts whether the drug was given. And you can see all these things, right? If you look at the top 10 reasons, things like aftercare following surgery, injury of chest wall, injury of sides of trunk, and if you give a DTaP medicine, then you give this. So essentially, this was given for all muscular pains. So these are the reasons why the drug was given. But at the 9th spot, you see heart attack. This is not the reason why it was given, but it was predictive. At the 9th spot, it was one of the top 10 predictors. 9th spot was heart attack. But the most interesting one for me is the first spot, which basically says abnormal glucose level. There was always a speculation whether these heart attacks were caused by spike in blood glucose level. And particularly if the person had diabetes and stuff, this would easily cause a heart attack. And so we, of course, based on this, we submitted several applications, there was a group called Observational Medical Outcome Practice, OMAP, that kind of, gave us funding to continue this direction. We have made many progress. But this was the study that made me realize that AI and machine learning can have a data-driven approach, in particular, can have a good impact in medicine. So with that, I'm going to quickly run through this. It's 7:30 in my time, but I think it's 1:30 here. So I will try and finish each of this in about 7 to 8 minutes. So I won't bore you more than it should be. Okay. So as I said, at the foundation of everything, you need some model that is working brilliantly. And for us, and again, this is an advice to grad students, if you have tabular data, if you have relational databases, try gradient boosting. It works beautifully on these problems. Okay, so gradient boosting, the idea is very simple. You have an initial model, you take the data, you make predictions. The difference between data and predictions is the gradient. And then once you get the data gradients for that, you fit the model to the gradient, not to the original data. You fit it to the gradient. You will learn a new model, make new predictions, new gradients, and go until you converge. Okay, let me just ground this out with a simple example. Let's say I'm predicting who has diabetes. Okay, I told you I have diabetes, right? So I have diabetes. Navi is very healthy. He doesn't have diabetes. Now, the data, let's say my initial model is predicting that I have diabetes with 0.6 probability, and Navi has diabetes with 0.45 probability. Okay, because it's closer to uniform distribution. So 0.6 for me, 0.45 for him. And I plug that in. Because mine is a 1 minus 0.6, 0.4 is my gradient. For Navi, it should be a 0 because he's a negative example. 0 minus 0.5, 0.45, negative 0.45 is his gradient. Okay, so and then now the next tree is not going to predict 1 and 0 anymore. It's going to predict negative 0.45 for him and 0.6 for me. So I'm learning a new model. Now my new tree, putting the two trees together, maybe the new model says Navi has diabetes with 0.23. For me, it is 0.8. So for me, now the new gradient is 0.2. For him, it's negative 0.2, and it continues. Okay. But in some cases, only the positive examples will be brought closer to 1. Then in some other cases, then so some tree might learn to better fit positive examples. Some tree might not better to fit negative examples, and so on. And so the final model is the simple sum of these trees. Okay. And it works beautifully. It is this is basically the idea of boosting, right? You make a mistake, you boost that mistake, find where you're making those mistakes, boost the model so that you focus on those mistakes. That's boosting. But you take that boosting through gradients. And so that's why this is called gradient boosting. Okay. And it works again, there are many forms of it. The most popular form is XGBoost. but the real work was done in 2001. Honestly, one of the best papers I've ever read by Jerome Friedman on the gradient boosting machine. Okay, so what can be learned? Again, multiple types of distributions, multinomial, Gaussian, exponential, Poisson, and so on. So we have learned many of these distributions. Again, that has led to a lot of publications. But again, the boring part is with relational data, I've learned multiple types of models. Most of our PhD students' work is on this. But the thing that I'm more proud about is the fact that we deployed this on multiple applications. So the cardiovascular study is what I'm going to explain next. But we've also published in Alzheimer's date study with neuroradiology experts. We have done in image segmentation back in the day. And now, actually, we have done a recommendation system that even won the IAAI Best Paper Award, the AAA Best Paper Award this year. We were able to build a recommendation system. And the cool thing is this is an open source software that people can use. When there is a call for proposals, we match researchers to those proposals. So in a university, I don't even know Professor X exists. And Professor X could be the best collaborator for me, and the system makes that recommendation automatically. And now it's deployed in 3 different universities. And so it's working very well based on this. And again, going back to that 1985 to 2005 data, Cardia, we were interested in predicting. The first step was coronary artery calcification, which is the calcium deposit on the left artery, right? The most boring part of this is, yeah, we got the best results. But the interesting part is what these results mean. So we have a way now, this was published last year, where we can take these 10 different trees and combine them to a single tree and give you the answer. Okay, so there is a very nice paper by Sivan Yan, Rani Kardan, Prasad Tarepalli, Saket Joshi, and myself on this, how do you combine these trees to a single tree analytically. So it's based on model compression and it works beautifully. And I want to show you just this result, okay? This is in predicate logic format, so don't try reading it too much, but stick with me when I go through this. So this is basically saying, if this is a male, and we know that men are more prone to cardiovascular events than women, okay? But it's more lethal in women than it is in men. So I know of a male who has survived 6 heart attacks. But very rarely women survive more than 2 heart attacks. Okay, so it's much more lethal in women, but the prior chance of women getting it is much lesser than a man. So that's the trade-off. And so you come there and then you look at this person and you say, well, even in 1992, they were slightly on the older side. Their cholesterol was slightly high and they were smoking. Then there was a 97% chance of a calcium deposit 20 years down the line. As against 25 years down the line. Sorry. As against somebody who has never smoked and is a female. Okay, so they have a nearly 20 times chance of having a lesser cardiovascular event. The other thing that we also saw, and these results have shifted up, the AUC, ROC, ignore that for a moment, is that adding more and more data did not help. So beyond ES7, so if I know their behavior by their mid to late 20s, most of them remained constant, at least in that population. So it's not like their behavior in the later years changed much. It's depressing to know that, right? That's where we can interfere, make it better, and improve their cardiovascular health. I also looked at only socioeconomic data throughout all the clinical data, and this was very cool. So again, please don't try to parse it. It might send your head spinning. But it essentially says this person doesn't have a job, smokes regularly, doesn't have a residence. In this case, it means staying with parents and has children. So no job, has children, and lives with parents, smokes regularly. You can see stress level is high. There was like a 90% chance of a cardiovascular event. As against somebody who has a job, false means has a job. Let me go down this path. Has not smoked cigars and has been married for 10 years. I can't say happily married. There is no data on that. Okay, they have been in a stable marriage for 10 years. They have 9 times lesser chance of a cardiovascular event because of the fact that they have a slightly, I don't know, I want to say less stressful life. But people who are married may disagree. But my point is that some types of stress are not as good as the other types of stress, maybe. Okay, and then we built all these temporal models and are trying to understand where we can intervene, how we can intervene. Obviously, I cannot go and say don't have as many children. right? To a person who's already has 5 children, don't have 5 children. I go, no, that doesn't make sense. Or, get pregnant when you're 18, not when you're 38. That's not the right intervention. So we want to figure out the actionable interventions. At the same time, if I just come and somebody comes and just tells me, Sriraam, quit sugar tomorrow. I'm like, no, get out. Right? I'm kind of addicted to it. So I need to, come out of it slowly. So you have to figure out how to do this correctly. And so we have been building all these causal models and other types of models. Again, I can talk to you about it after the seminar if you want. The cool thing is all our code is open source. Everything is online, and we have released some snippets of the data, not perfect data sets because we cannot do that. But I can tell you how to get access to those data in case you're interested. Reach out to me. It's all in there. We have been maintaining this web page, and we provide all bug support and issues as well. I'm going to pause for a minute to see if there are any questions, because let's make it interactive. If you don't, I can push ahead. Yeah.
Yeah. So these were decision trees, obviously. I mean,
yeah.
Was that the first choice, or what did you have?
No, we tried a bunch of other things, all the way from logistic regression to support vector machine, to back then neural networks, and the boosted trees gave the best result. Even bagging did not give me the results that boosting gave me, and because there are some nuances that I kind of pushed under the rug, like class imbalance. You can control it better with boosted trees than with bagged trees. And so instead of doing resampling, we were able to just control it based on giving that as an input. And I'll talk about it in a little bit. So we did try many algorithms, and boosting was the one that seemed to work. Yeah.
I sort of want to ask about the actions or actionable states. So is it that there's, for that, how do you determine which?
So let me just give you an easy example, right? When a diabetic, Sriraam, hits 40, and I've been diagnosed with diabetes before I was 40, then it is, no matter what, always safe to give me a statin, extremely low dose statin, for the next whatever years. I don't know how long I'm going to live, but let's say 30 years. For the next 30 years, I'm going to be on statin, a low dose statin, to prevent a buildup of cholesterol. And so that is a very easy, actionable intervention that one could make. And of course, somebody could come and say, okay, can you change your behavior? This is the, I was put to talk to a dietitian. They put me in touch with somebody who was a physical trainer to see if they can get me some exercises to particularly focus on reducing your blood sugar level. So those are the types of things that we were looking at in the cardiovascular health. Cheap interventions, not expensive ones, right? So like aspirin is another nice thing, right? If you are diabetic, you have cholesterol, and you're over 65, always have an aspirin next to you. It's just to be safe, right? Always have an aspirin next to you. It's a very simple intervention that you can provide to prevent anything serious. And so the point is that there are some reasonable interventions that what could come with, and those are the ones that we are targeting. Not like, when do I put somebody on a ventilator or an ECMO? Those are harder problems. So I thought I saw another hand. Yes.
Yeah, I was wondering if you could comment on whether there's complexities or deficiencies in learning from historical data, because there's a changing cultural context. People have different diets, they have different habits.
Yeah.
Things like that.
Yeah, that's a great question. I mean, yeah. So my parents strictly believe that me moving to the US is the reason for my diabetes. So I'm with you in that perception, and it's probably true, right? I mean, I see high fructose corn syrup in everything. I did not know that 20 years back when I moved, and I know how many sodas I consumed, and So yes, it matters. But for this data set, again, that's why it's a little, you cannot just generalize very quickly from this data set. For this data set, it was pretty homogeneous because these guys were in the same area, right? And we still haven't gone too vegan in the US. We still haven't eliminated a lot of fatty food, right? And we still haven't eliminated ultra processed foods that much. So we haven't changed a lot in the last 40 years, and this population hasn't changed a lot. So the conclusions on this population is much more robust than, let's say, somebody like Sriraam, who is been around but at the same time, things keep changing. I mean, it's not a joke when I say this. I have measured my blood glucose level before I go to India, and my weight and BMI. And then I spend 3 weeks in India, I come back. Everything is on the lower side, right? And I still eat more. I mean, Indian sweets are still sweet. I eat more. But something is there, the difference in that. I can't put my finger on it. Same thing with Europe. I come to Europe, spend 10 days, I go back, things are on the lower side. But the moment I get back and they start eating, things go. I don't know why. We haven't figured out why. I mean, we can just speculate at this point. But I'm with you. When we draw these conclusions, we have to be careful and we have to be responsible when in making these conclusions. But asking somebody to exercise and take a low dose of statin, irrespective of the culture and the diet, I think is still a valid thing. And if anybody, for instance, has lost a parent when they were below 60, asking them to check their cholesterol levels every 6 months, their sugar level every 6 months, is irrespective of the population that you talk about. So to me, there are conclusions that you can draw that you can generalize across populations, but then you have to be wary of what is specific to that data set. In this case, the homogeneity is in that data set. So that's a great question. And that's why I don't want to make like very tall claims. But at the same time, there is potential for making these things. So great question. Thank you. Yeah.
When a new drug comes along as a potential,
right,
how do you incorporate that into
the learned model? Yeah. So that is where I think things like LLMs can come in, because even when it comes to new ones come in, there's a lot of published literature on, they do the clinical trials, the results of the clinical trials are being published and stuff. So we have to get them into the market and then keep updating the model as we go. So to me, there are some positives and negatives, but like this, what is it called? I can't pronounce it correctly. Ozemiac or whatever that is, the injection that you can take instead of insulin once a week that brings down blood sugar level drastically. People use it for weight loss. We have not quite understood the medium term effects of those, because yes, they do bring what is being targeted down, but would it have the same effect as Bextra? I don't know yet. So the Bextra and Vioxx are classic examples. When they came out, we thought that they can cure muscle injuries, but then in a few years we saw that they were causing a lot of heart attacks. So we need to understand this trajectory clearly. And I think this is where I'm advocating the use of LLMs and stuff to keep on top of the published research. Can we summarize these research? Is there any finding anywhere where there is an negative observation based on this, and use it back into the model? So again, it's probably feeding into the second part where I'm saying data is not everything. Domain experts' knowledge is important, and so I'm seeing that as a domain expert knowledge. Okay. So again, data is not everything. We need more. The most important type of information that a domain expert can give you are these qualitative constraints. So they can say, as cholesterol increases, the risk of heart attack increases. As blood sugar increases, the risk of heart attack increases. Okay, and you can say more nuanced things. Higher HDL level with a higher A1C has a lower risk of heart attack than lower HDL level with higher A1C. Now you see that you're not just talking about one risk factor to the disease, or in machine learning terms, one feature to the target, but you're talking about how multiple risk factors interact with respect to the target. Here is the most important thing. I am not setting the parameter. I'm not setting what is the weight. I'm telling you in some sense the direction of this distribution. I'm saying as A increases, B increases, moves the probability mass function this way. Let's say low to high. It just says the probability mass function moves this way. So the point is that these things can be easily written down as if then else statements, and then you can actually pass them and put them as constraints. The second one is precision versus recall, and this is something that everybody has to remember. When I'm predicting, let's say, a job recommendation, and I use this example for 10 years and 9 years, and it's still true. I always get this email once a month saying LinkedIn has found some job recommendation for you. And of all, in the past 9 years, about 90% of the times, it points me to this one grant, which says Precision Health Initiative in Indiana University is looking for a postdoc. Okay, first, been there, done my time, over. Great, by the way, that was the best part of my life. I love my postdoc, but I don't want to do that again. Two, I'm the PI of the grant. So it wants me to be a postdoc for the grant for which I'm a PI. Why? Because it's trying to maximize clearly some recall function. I don't want everything that is relevant to me, but the top 7 that you give me better be very relevant to me. And I honestly do not know what is relevant to me at this point. Okay, because I don't want an administrative role and I don't want more changes. So I don't know. But so maybe I don't need anything from LinkedIn. But the point is that recommendation engines should be targeting here. Opposite is for Ebola, right? Because I'm from US, I can talk in terms of dollars all the time. the easiest way to think about it is, if I have a false, let's say false positive, what am I going to do? I'm going to quarantine this person for maybe like 5 days. What will this person do? It's typical in US. They'll go out and sue me. Okay, so I lose $1 million, $2 million, $10 million, some number. But I let this person out with a false negative. What happens? A local, whatever, epidemic happens in that local area. Now, there, I need to maximize my recall. So what we really need are systems where you can turn the knob. And this is maybe answering your question when you ask me that you can just turn that knob in our algorithms between precision and recall. And I say, here I want to maximize precision. Here I want to maximize recall. Here I want a combination of both. And that knob should be turned and the algorithm should work. And those are the real correct algorithms. The other one, which is extremely important, is we don't think about it carefully, is when it comes to personalization, is the idea of preferences. I have realized that doctors who are on the older side are a little more conservative when it comes to giving medicines. They want you to modify your behavior, see what, because they have a lot of experience. They've seen so many things in their life. They know that just increasing my tablet is not going to change things. They want me to change some behavior. We'll say, take it slowly, it's not that urgent. But then I've seen younger doctors. I mean, I went once to this guy who saw my blood glucose level go up by 0.2 and doubled my metformin dose. I was at the maximum for a blood sugar level of something like 6.3. Okay, so you can see that they have different preferences in which they approach the problem, and they have reasons for their preferences. We should be able to take that in as well. And the other one for which Navi is really famous for is the idea of privileged information, where you have some extra information during training that you don't have during deployment. Okay, we have I'm going to talk about this clinical study on adverse pregnancy outcomes, where we are putting these women, we are giving them smartwatches so that we can monitor their sleep. They are on, some of them are even in smart homes, so we can have more data about these people. Whereas you deploy, during deployment, the OBGYN is going to just look at their electronic health record, a bunch of image data, and they have to make decisions based on that. In this case, for instance, this is for Alzheimer's, you can have electronic health record, you can have MRI images, but you can also have questionnaires, right? And cognitive questionnaires in particular, and some smart devices. These are there during the clinical study. But during deployment, when the neurologist is looking at this person, they only have the electronic health record and the images, and they have to make a decision based on this. So the point is, you have this extra data. What do you do with it? You can either learn using these data, treat them as latent during deployment, or you use them as constraints to better guide the model to a better solution. And so Navi was the one who inspired me to do this, and we've been doing this. And I can tell you, in medicine, this kind of an information is extremely important. You have a lot of data during clinical studies that you don't have. And again, I'm going to sweep how we do it under the rug, because we have a varied audience, but the idea is very simple. You basically take a trade-off between data and the kind of knowledge, and figure out which is more important where, and figure out how they change. And again, the code is available online. You should be able to use it, and you can see that it's robust in some sense to this choice of lambda, because which is kind of controlling the trade-off, and it works well on graphical models, blah 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 blah. Both. Okay, boring. Let's go to what I want to say, which is the new moms to be. We were looking at 10,000 nulliparous women with 8 centers around the US. Nulliparous women who are pregnant for the first time. Okay, and 44% of the women had gestational diabetes. We looked at a bunch of risk factors. And we were trying to figure out how to create models that are interpretable, explainable, and provide actionable outcomes. One of the ways we were thinking was, can we get some domain knowledge? Again, remember, the domain knowledge is of the qualitative constraints, which essentially says as A increases, B increases. Here it says, as the polygenic risk increases, which is the prior risk of having diabetes, the risk of diabetes increases, and so on and so forth. And we were able to encode whatever the domain expert told us into a very simple inverse naive Bayes model, and simply learn the parameters. Turns out we were as good as gradient boosting, which was basically the best at that point. So you actually have a very simple interpretable model that you can combine to get something that is as good as the Bayesian networks. We are also working on these so-called probabilistic circuits or deep tractable models, which are essentially sums and products of distributions. I was talking about this yesterday in Navi's group, but these seem to be working well. So it's a stacking problem of where I'm going to, the pluses really represent mixtures of distributions, and the products represents independence of distributions. So you can say things like there is a food and diet, diet and exercise that is probably independent of the family history. Okay, so these are two groups, so they go in two different groups under a single product, but then they can be summed out and so on and so forth. So we can get all these structures out of this, and we are, we can learn complex data distributions. We can efficiently reason. Again, I'm pushing all this under the rug, and I'm just going to say what we can learn. All I want to say is that this is not just plugged out of thin air. These tractable models actually can be trained using neural network methods. So essentially, you can have backpropagation, end-to-end training. So you can actually get good results using this on many of these large problems. And what we have shown is that you can actually learn more robust models. Again, I'm skipping all this because I really do want to get to what I want to say. Okay, but the thing is that the point I wanted to say, as A increases, B increases, simply becomes a constraint in your conditional probability table. So while evaluating the lower distribution, I can plug in these constraints. And as you can see, what we can do is we can learn, this is KI is knowledge intensive learning. This is the original learning. We are learning models that are smaller, which means smaller models are more easily interpretable, and most importantly, applying Occam's razor, they probably fit the story better. But we actually get the lowest mean squared errors on the queries. But the cooler thing is, if you learn a model only from data, and this is the model that is learned from data and knowledge, you can see that there are some important differences. So here, BMI seems to be the most important factor. Whereas just putting a knowledge that says PRS influences gestational diabetes, always across all the runs, across all the data sets, brings PRS to the top for us, which is how clinically they think about it, right? Before, once the woman comes and says, okay, I'm pregnant, the doctor is going to ask, well, what is your family history of diabetes, right? And that is captured here, right? While these are their behaviors and things later. And so we were able to build these things, and we can also generate, we can also explain these larger models using what is independent from what and so on. For instance, we came up with an explanation that says, once you know that this person just doesn't have gestational diabetes, then knowing anything about BMI is not going to explain anything for me. Whereas if they have gestational diabetes, there is a causal explanation that we can tease out based on this. And again, horses for courses is important. So I want to say here it is simple association rule mining. And this is a paper that we published in JAMA Network Open just last year. Simple association rule mining showed us a lot of interaction between polygenic risk score and exercise on diabetes. So if you have a high risk for gestational diabetes, you should exercise. But exercise is a complex thing. I want to make it very, very clear, right? So if a woman has been exercising a lot before pregnancy and they continue exercising, it's great. If they have exercised some before pregnancy, continue the some, right? If they have exercised some, just don't suddenly decide, oh, I'm putting on weight, so I'm going to exercise more. Actually, that increases the risk of many adverse pregnancy outcomes. So, back in the day, old age wisdom says, oh, you have to take rest when you're pregnant. Some of it is true, right? But some of it is not. So we have to be very nuanced about this and understand this. Same thing even with men, right? Like men typically think, oh, it's okay. It only depends on the woman's age. Turns out that there's enough research that shows that anybody who's actually, if the male is over 40, specifically if the men is over 40, there is a higher risk for ADHD and autism in the kids that are born after 40. So there are a lot of these nuances that we have to understand from data that we have to, again, the question of how do you generalize it to overall populations? I think those are the questions that we are doing. And I think that this is one way of providing information back to the experts. So for instance, like I talked about, we're going to explain it back to the expert. So we asked for some inputs from the expert, and then we gave some output back. We say things like, let me just pick one of these. I also realize I'm old to read these fonts. Let's see, data alone, okay, Quake and the expert, okay, prior knowledge is wrong. So for instance, we found a relationship between BMI and education that experts did not believe was true, right? This one right here. Expert did not think that was true, but the data clearly showed that there is a relationship between BMI and education. Again, remember, we are in a college town. So in and around the area. So if they are very aware that, they want to make sure that their BMI is lower, and they try to do that before this. So the point is that you can learn this. And I'm going to actually wrap up my talk with just one final point, which is that one of the advantages of these models is that we can do what we call as anytime prediction. We can predict things. Let's say this is actually one of the things that got a lot of attention in the US, because we are predicting heart attacks in children 12 hours before, all the way to the point of heart attack, right? And we are just looking at the data from 12 hours before, then from 9 hours before. Actually, we have even had points in between, then 5 hours before and 1 hour before. We were able to make reasonably good predictions. And we developed an anytime algorithm where the doctor can stop and ask, what is the probability of this child having a heart attack in the next 5 hours? And we looked at only electronic health records. And we were able to make this prediction, again, using gradient boosted trees. And now we are building these probabilistic models for building causal models for figuring out how to intervene and stop these heart attacks. Okay, with that, I want to also, just say that one of the nice things about all these things is that we can put this together in a model where we can explain things. So for instance, we are looking at 3 types of procedures: angioplasty, valve replacement, and EKG. And we are trying to predict who is going to get all 3, who needs only 2 of them, who needs only 1 of them, who needs none of them, before they are even seen by the doctor. So in some sort of a triage type situations where we can say these persons need this by just looking at their data as they are entering. Okay. And again, got some good results on this. I'm going to skip this, but I really think that we are building, this is work with Christian Kirsting. We are trying to think about idea of building a never-ending learning and reasoning system, which essentially learns from the data, continuously interacts with the expert, and evolves with the as data changes, as knowledge changes. As newer medicines come through, we should be able to build our causal models, refine them, and learn better. But also we should understand and talk about whether are we going to talk about the results in a population level or a subpopulation level or a particular race group, in my case South Indians, and see if you can get a better result. Even South Indians, right? That's the funny part. South Indians have a higher risk of gestational diabetes than North Indians, than Western Indians. Why? I mean, Western Indians seem to consume a lot more sugar than South Indians. There is something in the genetic makeup that we have not fully understood. And so, we don't know these things, and we need to understand this better. What I'm always in favor of is not only having interdisciplinary research, but also interdisciplinary research. What I mean that is even areas of machine learning and AI should come together, right? It's not just one area. You can work in your silo and get your grants and do your things. But, people need to come together and, work together. Again, a lot of things, but we are out of time, so I want to stop here. But my final thing is that no ring to rule. I am a big Lord of the Rings fan, so there's no one ring to rule them all. So we have to really be careful in what we choose. The algorithms are extremely important. It's okay if the model is not deep, as long as the reasoning is not shallow. Okay, so don't go for deep model just as a de facto, because many of these data points, look, I got a call from my collaborator, Dr. Lakshmi Raman. She said, Sriraam, we have a lot of data for you. I think I told this yesterday. And I said, great, a lot of data. We had 140 patients so far. And she said, lot of data. I'm so excited. Yes, how much? She says, 2 days worth of data. I said, yes, but how many people? 25. So we have 25 rows and about 500,000 columns. And is this what you want your big data to look like? Probably not. Anyway, human is an ally in learning, and AI systems should figure out how to use it. And again, when you design these, please keep that communication is the crucial aspect. We need to deploy these in real problems, not just hype it with LLMs. And one of my recent passion has been on figuring out if we can, when a new student comes and says, I want to learn about neural networks, right? You don't want to say, okay, start from the 2013 paper. You want to go all the way to Rosenblatt papers, 1965. Let's get these papers out. Then we'll show the Minsky's paper on perceptron, limitations of perceptron. And then we'll go from there, right? So we need to show that, and we need to build this history, and we need to do that. Now, of course, also learning from multiple experts. It's funny because you talk to one doctor, the other doctor doesn't agree with this doctor. But they're both correct in their own ways. And we need to understand why, when should we trust one doctor over the other? It's extremely important to understand safety, ethical, fairness constraints, put them in the model. You can't just release the data, release the model. If it jacks up an insurance for another person, it's probably not the right thing to do. So we have to think about this. And of course, multiple modalities of communication. And the root of all is, can we learn something from these experiences? So with that, I am done. I can answer questions. Thank you. And this will take you to my lab. Yes.
I'd like your thoughts on, it's interesting your thoughts on, if you like, practical implementation, how these algorithms should be, if you like, embedded in the working day for a clinician.
Right. In my opinion, it is like a personal assistant, right? Not like Clippy. Okay. Again, people remember Clippy. We don't want a Clippy here, but we want to have a system which observes the human performing decisions and then tries to understand why these decisions are performed and then gives it back. So in my practical view of it, I think it should be implemented inside the electronic health record, where some sort of a color-coded warning comes up, some sort of a, when I just enter this, you pull the relevant data. Sriraam walks in with an ankle injury. Pull the data that he has diabetes. That should be the first thing that this person should know. And so pull relevant data, maybe my latest A1C score, so that the doctor can make an effective decision. So the way I view this is an integration into the electronic health record system, where the relevant information is being pulled in. Second thing I always tell the doctors, imagine you spending 10 minutes with me instead of the 2.5 minutes that you do. Why? Because the rest of the time, all they are doing is, this is what I observed, this is what they got. They're dictating it back to the system. But it should be done automatically. You just have a camera in the room. You should be able to get this information, put this in, you're done. Right? Anybody who sits there, who is not a medical expert, can understand what is going on. You should be able to do this, identify the ICD 9 or 10 codes, automatically put them in. So to me, that is the way I see a practical implementation. And I think that's where, if we have healthcare companies that actually do this integration of assistive systems inside electronic health records, I think we'll go a long way in making healthcare much more effective. I don't know if I fully answered your question, but that's the way I imagine the practical side.
Thank you.
Yes.
Yes, you talked about making the system such that a healthcare expert can communicate back.
Right.
What do you think is the characteristic that the system needs to have for this to work? Are you thinking all the way to kind of speech recognition, natural language processing, everything automated, or is there something?
In my head, the long-term view is that I need to have speech recognition, then have NLP, then have some sort of an ontology mapping where I take this and map it to the corresponding, as an answer to his question, corresponding to ICD 9 codes and ICD 10 codes, and figure out how it is stored in the database and then map it back to the system. So that's my long-term view. But in the short-term view, I'm thinking just even natural language, right? They just enter 3 or 4 things. You fill in the summary, right? Met this person, did this, this was the diagnosis, this is the thing. And then they are writing these long summaries, at least in the US. You see that they have this half-a-page summary of what they have done for you. And that is a waste of time. You can remove that burden off of the doctors, move it to this thing. I don't know here, I'm not been to a doctor here, but in the US, the nurse comes in, they take your measurements and they go out. The doctor comes in, nobody's there in the room, you and the doctor, and maybe your family member. So, I mean, there is that discrepancy where they don't get that information directly into the system. Maybe even just having the nurse write down the whole thing might save their time, but somehow they don't do that. Maybe for patients' privacy, I don't know the reason. But if we have systems that can automatically transcribe that into the formal language that is used to describe these things, I think that should be sufficient. But that's the first step. I think the longer step, I really want a camera. I just think, just have a camera, everything else should be automated. And we should be able to do that. But again, many parts need to come together to get that. Any other questions?
So thank you everyone, and Sriraam will be around here still for 2 more hours. So in case if you are interested, thank you everyone. Thank you, Sriraam.
Thank you.